So this is more review for exam 3. Use the first derivative to find all critical points, and use the second derivative to find all inflection points. We have a special deal going on here. Remember, we have a special deal on cubics. It's a cubic. Okay, so all you can do with cubics is you can either have this kind of cubic, where there's an inflection point going up or down. So you can just multiply this by -1, it's the same. Or you can have a horizontal inflection point, which is also a critical point. So we have a point of inflection, critical point. Here we have a point of inflection, no critical points. Or we can have, in a line, we can have, whoops, we can have a critical point, point of inflection, critical point. Again, you can multiply by -1. But those are the only things that your cubics can do. So you look for one of these three cases to be occurring and just sort of use the calculus to justify what you're doing. But since it's a special case, it cuts back our workload tremendously. So we go ahead, take the derivative, set it equal to 0, and this is just a parabola. So the vertex is minus b over 2a, and so it's actually 0. But let's say we didn't notice that. So we can just say 3x squared is 4, x squared is 4/3, and you know what, I don't actually care what the square root of 4/3 is. I'm sorry, you may think I care. I don't, because I'm a mathematician. All I care about is it's greater than 1, and it's probably less than 2. Yeah, it's way less than 2. That's all I care about. All right, but the important thing that it's symmetric on either side of 0. Okay, so these are the critical points, so we're going to classify them in a minute. Second derivative is 6x. Well, that equals to 0 if x is equal to 0. So 0, 0, it's very easy to calculate the y-coordinate for that, is the point of inflection. Now, if I hadn't said you had to find both coordinates for this guy over here, then you wouldn't have to. I usually don't care, but in this case I said do it, so you have to. Sorry. Sometime I have to eventually test you on these things, so this is one of those cases. So let's say f, whoops, I didn't really want to use red. F of square root of 4/3 is 3 times, what is, I'm sorry, I was doing f prime instead of f. It's a common mistake. We got to go back to this function. Square root of 4/3, and then we're going to cube that, minus 4 times square root of 4/3. And you may say, oh, she didn't care, we can stop here. But that's not true. I care about this. I care about the fact that I take 4/3 square root of it. If I cube it, it actually looks like this. So what do I care about and what do I not care about? Well, you just have to kind of learn. But these guys, alright, these guys together make 4/3. And 4, I'm going to convert it to thirds, it's 12/3. I need to get common denominators so that I can make this look more respectable. Now, to a mathematician, this is as far as you need to go. You don't need to simplify it anymore. And so we have a critical point. So we have 4/3, and the y-coordinate is 8/3 times square root of 4/3. Okay? Now we need to go, sorry I didn't leave much room here. It's actually easier to write with a pencil. Square root of 4/3 is minus square root of 4/3 cubed minus 4 minus square root of 4/3. Okay, so we have 3 negative signs stacked up. So we have the same situation we had over here, except with 3 negative signs. Okay, so one of them gets to stay, and the other 2 we ditch. We get minus 4/3 square root of 4/3. But this sign is also going to flip because this is going to have a negative sign on it. So it's going to come out and meet that negative sign. So you're going to have a plus 4 square root of 4 over 3. So since all the signs switched, it's exactly the same. And we expected this. We knew this was going to happen. So why do we know? Because we know that it's that special case of the cubic, and the two critical points plus the point of inflection together, they all have to be collinear. And so this is a very special situation. We actually know what's going on, and so we didn't really have to do this step, but we do. We have to do it to show that we know what we're doing. Okay, so let's plot these guys out, and then it'll be obvious which is the max and which is the min. Okay, we've got the origin, and that's going to be the point of inflection, and then we have some value. Think of it as 1, something a little bit more than 1. And then 8 over 3, you can think of that as negative 3. So 1, negative 3. So you want to think of this as being just ballpark. This is about 1. And if this is like more than 8, so it's like minus 9 over 3, so it's about minus 3. And so this is about minus 1, and that's about 3. Just for plotting purposes, that's good enough. So 1, negative 3 is down maybe here, and 3, negative 1. So this is what you're going to do in your mind, so you don't have a ruler, of course. So you're going to think of it this way. You're going to draw yourself those 3 dots. Okay, and then it's really obvious what's happening, because in the end, you see x cubed is going to dominate. This piece is going to be the most important piece. So what you're going to do is you're going to make sure you go off to positive infinity at the end. So now we have enough information to figure out what's going on. This is going to be the concave up part. This is going to be the concave down part. And oh look, this specific problem, I could factor out that x and find out actually where the roots are. And if we had done that first, we could have used our little quick plot method, and we could have gotten just this plot. Now it says use calculus. It says use the first derivative, use the second derivative, so we had to do it. But the quick plot would have helped reassure us that what we were doing is right. So there's a point of inflection. This guy is the min. This guy is the max. And since we've written them out up above, we don't need to write them down below, but it might be nice to write them down below. Okay, so we can go ahead and put a copy of these values down below if we really, really want to. So we can just take this guy and say, stick him down here, stick him up here. There we go. See, all done.